At 35,000 feet, lightning slams into the nose. A flash, a bang, but the plane flies on. That's not luck, it's engineering. Every airliner is struck about once a year, yet passengers rarely notice. Why? The answer lies in a tragedy that rewrote the rules. This is Wings and Wrecks. How machines fail, and what saves the people inside them. So why doesn't the bolt bring the aircraft down? And why did a strike just like it once tear an airliner apart? In 1963, Pan Am 214 was hit near Elkton, Maryland. The bolt ignited fuel vapor, destroying the wing. All 81 died. December 8, 1963. A Boeing 707 climbs into a dark, stormy night. 81 souls aboard. It enters a thunderstorm, and minutes later, everything changes. What was different about that aircraft, and what got fixed? The board determined lightning-induced ignition of the fuel-air mixture in the number 1 reserve tank, causing explosive disintegration of the left wing. All 81 perished. But the real culprit was something far smaller. The lightning itself didn't destroy the plane. It was a tiny spark, a millijoule, that ignited fuel vapors. The lesson: it's not the bolt, it's the spark. That spark became the focus of every safety measure that followed. How could a bolt cause such a precise, deadly ignition? Investigators sifted through frozen fields, piecing together the shattered 707. The left wing had exploded mid-air, the only plausible trigger: lightning. The bolt itself hadn't destroyed the aircraft. The board named a subtler killer, a spark that ignited the fuel-air mixture in the number 1 reserve tank. The exact pathway was never fully determined, but the implication was clear. The lesson: fuel tanks had to be protected. Investigators suspected improper bonding and overheating of the wing skin, a tiny flaw that turned a routine strike into catastrophe. That suspicion rewrote the rules, and the fixes are still in use today. Why didn't anyone stop it? A paradox. Lightning is immense, but the spark is tiny, a few millijoules. And the fuel tank, full of vapor, is a waiting bomb. The solution: make the tank too poor to burn. That's where inerting comes in. The answer is inerting, pumping nitrogen-enriched air into the tank, dropping oxygen below ignition point. Combined with the Faraday cage, the bolt is shunted around the skin. And even if a spark forms, there's nothing to burn. The lesson from Pan Am 214 is still flying today. Why do passengers often not notice a strike? The key is the metal skin. It acts as a Faraday cage, a conductive shell that carries current around the outside, not through the inside. The current bypasses the cabin and fuel tanks, exiting harmlessly. But what happens when the skin isn't metal? Here's the catch: modern planes aren't all metal. The 787's fuselage is carbon fiber composite, which doesn't conduct well. So engineers embedded a copper mesh into the skin, restoring the Faraday cage. The shield must never fail, even with new materials. But what about the 787, built mostly of carbon fiber composites? Carbon fiber is a poor conductor. How does it survive a strike? The answer: a copper mesh, woven into the skin, providing a conductive path. That mesh is the modern successor to the all-metal shell. This mesh restores the Faraday cage, shunting lightning's current around the cabin. Even with modern materials, the protection must never be compromised. What happens when a plane is struck? Pilots don't panic. They run a checklist, and after landing, crews inspect. Damage can be subtle: a cracked lens, a burnt control surface, a faulty fuel gauge. These checks are the final layer of defense. The checklist is thorough. They examine all external lights, looking for broken assemblies. They check flight control surfaces, and they verify the fuel quantity system, because a subtle mark can affect the next flight. It's a routine born from tragedy. Pan Am 214 was a tragedy, but its legacy is in every airliner today. The copper mesh, the inert gas, these are quiet monuments to that stormy night. And they work every day, protecting millions of passengers. But why is fuel vapor so dangerous? At altitude, the tank isn't full of liquid, it's full of vapor. A single spark, even a millijoule, can ignite that vapor. That's why the #1 tank on Pan Am 214 was the weak point. The vapor, not the liquid, is the real hazard. So a millijoule spark, barely enough to feel, can cause a catastrophe. That's the paradox of lightning protection. The bolt is huge, but the spark is tiny. Engineers realized they had to eliminate even the smallest spark. That meant redesigning fuel systems from the ground up. The first fix was bonding. Every metal part of the aircraft is connected with conductive straps, ensuring no potential difference can build up. This prevents sparks from jumping between parts. Bonding straps are now standard, a direct response to the suspected cause of Pan Am 214. But bonding isn't enough. Static electricity builds up on the skin as the plane flies. That's where static wicks come in, small metal rods on the trailing edges. They discharge static continuously, preventing a buildup that could trigger a spark. Every airliner has dozens of them. But what about the fuel tank itself? The ultimate fix is inerting. Systems generate nitrogen-enriched air and pump it into the tank, reducing oxygen to about 12%. Below that, fuel vapor can't ignite. Modern jets like the 787 have these systems built in, making the tank inert under all conditions. Engineers test. Aircraft components are subjected to simulated lightning strikes in labs, with currents up to 200,000 amps. These tests ensure that even a direct hit won't cause a spark. The results are baked into certification standards. And finally, there's the human factor. Pilots are trained to handle strikes, and maintenance crews are trained to spot damage. The checklist is drilled into them. This vigilance is the last line of defense, ensuring that even the smallest flaw is caught and fixed before it becomes a problem. Next time you see a flash outside the window, remember, you're inside a Faraday cage. The lightning passes around you, harmless. You're safer than you think. If you want to know why machines break and how crews fight back, subscribe. Next up, our next video.